Okay, we're going to discuss the Mos transistor today. The Mos transistor was actually invented later than the um, bipolar junction transistor. So nauna yung bipolar junction transistor sa Mos transistor. But right now, the Mos transistor is the most widely used transistor. If you take a look at integrated circuits nowadays, the transistors that are contained in integrated circuits are now more often than not Mos transistors. So to a certain extent, medyo ano no, hindi na kasing dalas ang paggamit ngayon ng bipolar junction transistor. Okay, the material that I'm going to present to you this afternoon is again just supplemental to the official material that has already been released through UVLE. Kaya ako tinanong kanina kung meron na nakasilip ng material because my material may not be the same, no? So I wanted it to be supplemental. So I'm also limiting what I'm going to present to you so that hindi kayo masyadong ma-overload, no? The official coverage of this module is the coverage of the slides that were published in UVLE by the handler that is in charge of this particular section. So what I'm going to present to you, if I present to you something that's extra, that's just for more insight on your part. So this first few slides that I'm going to create for you is really just extra. It's to give you a better perspective of the Mos transistor. So first of all, let's discuss structure. No? So ito hindi talaga ito part ng official material, okay? Because this is already part of the semiconductor physics of the Mos transistor. But I thought I'd just touch on it a little bit para ma-appreciate yun, mas ma-appreciate nyo yung Mos transistor. Okay? If I have a piece of semiconductor, top view, no? Top view. Let's say this is my semiconductor. Okay. And then, so let's say this is a p-type. Remember, this is top view. Okay. It's possible for me to create n-type within the p-type. So let's say this is n-type, and this is also n-type. Okay. I don't know if you recall before, but the difference between n-type and p-type are just in terms of the charge carriers that are present in the material. If the charge carriers in the material are electrons or negative, then that's n-type. If the charge carriers in the material are positive, then that's p-type. Okay? So p-type and n-type, no? So sige, let's color it a bit to make it look a little bit more interesting, no? So this is my n-type. Okay, let me draw a cross section here. So I'll get a cross section. Sorry. A cross section here. Okay. What will that look like? So this is my material. Okay. So ito yung n-type ko. So it will not be that deep, and also the n-type here. So this is n, and then this is also n. Okay. So ito yun. Okay. So remember that's a cross section. No? So this is a cross section. Okay. And then in the space between the n-type, I will put an insulator. Okay. This is silicon dioxide. SiO2, which is an insulator. And then I'm going to put contacts. So let me use red for the contacts. I'll put a contact here, a contact here, and a contact here. Okay. So these are now my terminals. Okay. This terminal I will call S. This terminal I will call G. And this terminal I will call D. S stands for source. G stands for gate. And D stands for drain. Okay. And then I'll have another terminal here, B, and B stands for bulk. That is the bulk of the semiconductor. Okay, so again, this is top view. This is the top view. Okay, and then this is the cross section. So if I take a look at the top view again, sorry, no? Top view again, dapat ilagay ko din dun kung saan yung mga contacts ko, no? So my contacts will be here. I'll have a contact here, and then I'll also have a contact here. And then my oxide, my silicon dioxide, will be here. No? So this is my silicon dioxide, which is again an insulator, and then I'll have a contact on top of it. Okay. So this contact is my gate, this contact is my drain, and this contact is this contact is my source, this contact is my gate, and this contact is my drain. Sandali, no? Sorry, this is a little bit wrong. No? Let me. Actually, the contact here should cover the silicon dioxide. No? So actually, yeah, this way. So silicon dioxide, and then on top of that, there's metal. So the red is the metal. Okay, this is what you call your Mos transistor. Okay, M stands for metal, O stands for oxide, and S stands for semiconductor. Yeah, there's a question here, no? The bulk, there's also a contact. Yeah, there's a contact connected to the bulk. No, that's also a terminal. So M is metal, O is oxide, S is semiconductor. That is the structure here in the middle. No? If you take a look at the middle, okay, pag tinignan natin yung gitna, I have a metal, so this is a metal, and then I have an oxide, and then underneath the oxide, I have semiconductor material. That's why it's called a Mos transistor, metal oxide semiconductor. Okay. So how does it work? How does it work? So let me draw again the cross section here. So this is my cross section. Okay. Have my metal. Okay, so this is my source, my gate, my drain. What will happen? What will happen if I connect a voltage between my source and drain? Let me call this VDS. So this is a voltage between source and drain. So I'll ask you, will current flow? Is current going to flow? Remember, this is N, and then this is P. Anyone? So no. Why? Why not? Yeah. The answer is correct, no? Yung mga sumagot na no current, why not, no? Actually, kasi if I take a look, saan dapat dadaan yung current dyan, ano? The current, if current is going to flow, it's going to flow this way. This way. Then from here, where will it go? Well, it will try to flow this way, no? That's how the current will try to flow. But if you take a look, this is N, this is P, and then N. So what is that? No, that looks like two diodes, right? So you have a PN junction here, and you also have a PN junction there. No, so if I take a look at this, what does it look like? It looks like this. No, I have VDS, and then I have two diodes. Okay, one diode is this way, and the other diode is this way. No, right? Because this is N, and this is N, and then this is P. Okay, so expect that current cannot flow. No? Because you have two back-to-back diodes. Okay. Now, what if I do this? Let me, para madali yung buhay ko, no? Let me just duplicate this slide. And let me just, sorry. Sandali ah. Ayaw magbura. Anyway, forget it. Let me just draw it again. No? Maybe I'll draw it a little bigger also. Okay, so this is N, this is N. This is my oxide. And then I have metal. Okay, actually metal din yung contacts, no? Metal din to, contacts, metal. Okay. So sabi natin, sinabi ko na kanina, that if I have a voltage this way, current will not flow, no? This is VDS. Okay. So this is my source, this is my drain, and then this is my gate. Okay, what if I do this now, no? Usually, no, this is connected to ground, and usually this is also connected to ground, no? The source is also connected to ground. Okay, what if I now apply a voltage between my gate and ground? I'm going to apply a voltage now between my gate and ground. Okay, and this is called VGS. Okay, the reason why it's called VGS implies it is the voltage from the gate to the source. No? But remember that my source is also connected to ground. No? Just as my bulk is connected to ground, the bulk. Something's wrong. The bulk is connected to ground. My source is also connected to ground. Now what's going to happen? No? Okay. I like to keep the colors. Anong mangyayari? Okay, this is going to cause an electric field to exist between this metal and the bulk. Magkakaroon ng electric field. What will that electric field do? No? Remember that this is p-type. This is p-type. No? But that has still electrons kahit papano. No? It will still have electrons. What will happen is electrons will be attracted to this area. Because of the electric field. No? You might think of it as this is a positive voltage, so the electrons are being attracted to this positive voltage. No? Remember, electrons are negative, so they will be attracted to the positive terminal. So yung mga electrons pupunta dyan. Ano ngayon ang mangyayari? No? Magkukumpulan dito yung mga electrons, and this will become N-type. This becomes N-type. When that becomes N-type, current can now flow this way. And you call this now a channel. This is now called a channel. This area that was created that became N-type because the electrons were attracted to that area, okay, is now called a channel, and this is called an N-channel Mos transistor. No? Or in short, just an Nmos transistor. Okay. However, for channel to be created, VGS has to exceed a certain threshold voltage. So VGS should be greater than or equal to a certain threshold voltage, which we will call VTH. And this is the threshold voltage of the MOS transistor. Okay, so this is now ID. This is ID. If VGS is less than VTH, ID will be equal to 0. There's no effective channel, no channel formed. Okay. I saw some questions. Yeah, I don't know at what point you asked your question, Mark. Maybe you can verbalize your question. What do you mean by same N type? Dun sa mga nagtatanong, if you want me to be able to answer right away, you have to shout it out, because I don't notice the comments right away. Okay. Okay, and then si Rick, what do you mean by Thevenin voltage? I don't. No. VTH is not Thevenin voltage, no. VTH is threshold voltage, hindi Thevenin voltage. Don't mistake this to be Thevenin voltage. It's a threshold voltage. It is a parameter of the transistor. No? So this is a transistor parameter. Okay. Okay. So for the channel to be created, again, this VGS has to be greater than or equal to a certain threshold voltage, which we call VTH. The MOS transistor threshold voltage. If VGS is less than VTH, there's no channel that will be formed, and your current is going to be equal to 0. Okay, any questions so far? So very qualitatively, that's how the MOS transistor works. In other words, you can get current to flow only if you apply a gate to source voltage. Okay. Yes, Tom, please.
In that schematic flow, are you shorting your drain and source since you don't have any resistance in between?
The drain and
the source.
No. The channel will have a resistance.
Okay.
It's not shorted. The channel will have a resistance.
Thank you.
Yeah, otherwise, kung walang resistance yan, di infinite yung current na magfo-flow, di ba? Yeah. That's a good question. Thank you. I need another slide now. Okay, let me do this. Let me try to plot what I of D is going to look like as I increase VDS. In other words, looking at this, so this is VDS, the drain to source voltage. This is I of D, the current that flows into the drain. So this flows into the drain. As I increase VDS, how will this ID increase? That is assume VGS is greater than the threshold voltage VTH. Okay, so this is related also to the previous question. So obviously, pag VDS is equal to 0, obviously I sub D is going to be equal to 0. Now, what happens if I increase this voltage? Okay, so I just mentioned as a response to the question, this acts like a resistor. No, it's not a short circuit. So if I increase this voltage, I expect the current to increase. No? Although it's not going to be a linear resistor. No? So this is going to increase somewhat. Okay, there's going to be a slight curve. You know, at some point, however, increasing further the value of VDS will not cause I sub D to increase further. At some point, this is going to become practically constant. Okay. So here we have identified two modes of operation of the MOS transistor. Okay. You call this the linear mode, and this is called the saturated mode. The saturated mode is when further increasing V sub VDS will not cause an increase in I sub D. The linear mode is when it is acting similar to a resistor. So you sometimes also call this resistance mode. No? Resistance mode. Now you might ask, bakit nagkakaroon ng saturation? I don't want to go into the semiconductor physics of that, no? But maybe a very, very short explanation. The reason why nagkakaroon ng saturation is because VDS has an effect on the electric field. No? I said that these electrons are attracted toward the gate or toward the underneath the oxide because of the electric field that is set up by VGS. But that electric field is not independent of VDS. No? As you increase VDS, that electric field decreases. No? And what happens is, at some point, the electric field will sort of be canceled out, almost be canceled out, so that further increasing VDS will no longer increase I sub D. You're going to learn more about that when you take up your semiconductor physics courses. Okay. So at what point does it change? Okay. When does it go into saturation? It goes into saturation here when VDS is greater than or equal to, sorry, when VDS is greater than or equal to VGS minus VTH. Okay, that is when it goes into saturation. So here, this is the linear mode. So here VDS is less than VGS minus VTH. So this is for a particular value of VGS, no? Let's call this VGS1. So when VGS1 minus VTH is greater than or is less than or equal to VDS, magsasaturate siya. What happens if I decrease VGS? So if you decrease VGS, this curve will just become lower. So this is VGS2, which is less than VGS1, and so forth. Okay, something like that. Okay, of course, all this has to satisfy this condition that VGS is greater than VTH. Okay. Now, when it is in saturation, notice that it is like a controlled current source. And in fact, Is of D is equal to a constant K times VGS minus VTH squared. Okay. That is going to be the value of Is of D. No? It's almost constant. It's not dependent on VDS. It's going to be a constant K times VGS minus VTH squared. No? On the other hand, when you're in linear mode, Is of D is going to be equal to, now in linear mode, the current is going to be a function of VDS. So this is going to be 2K, this is VGS minus VTH minus 1/2 VDS multiplied by VDS. So those are your two equations that govern your MOS transistor. Now this is the circuit symbol for your N-channel MOS or your NMOS. So this is the gate, the drain, and the source. Okay. The arrow just depicts the direction of current. No, it is flowing out of the source. Ito yung arrow. No. Now when your bulk is connected to your source, so remember, no, here, no, this is usually connected to ground, so this is also usually connected to ground. In other words, the source and the bulk, very often they're connected together. Then we have a simplified schematic symbol. This is the simplified schematic symbol, where we no longer show the B. So when you see this symbol, the assumption is the bulk is connected to the source. And very often that is connected to ground. Not all the time. Huh? I'm saying not all the time, but very often that is connected to ground. Okay. Now there are certain instances when the bulk is connected to ground, but the source is not connected to ground. Okay. Are there any questions so far?
Sir, in the previous slide, is there a point where increasing VGS doesn't increase the current anymore?
Ito na nga yun. Increasing VGS?
Yes, sir.
Theoretically, no. Theoretically, as you increase VGS, let's see. I have to check on that, no. That's medyo malalim na yun sa physics, no. But theoretically, if you increase VGS, then you increase the concentration of electrons that are going to this area. Okay. So that's going to make the resistance of this area smaller, and that's going to increase further the current. But if I recall now, I think there is a limit. No, there is a limit. No, and then the other thing about increasing VGS indiscriminately is there's such a thing in semiconductor as breakdown, where the molecules, how do you say it? No, the electrons are just yanked out of the atoms, no? And then the structure breaks down. But in terms of what that limit is, I have to check on that. I have to review I have to review my semiconductor physics. I'm sorry if I wasn't able to answer it very thoroughly. No? Okay. So this implies that there's another type of MOS transistor. There's also a P channel. And then the symbol for the P channel nagbabaliktad lang yung arrow, no? So the arrow is this way. Okay, yung P channel, if you take a look at this, ang semiconductor mo is N-type, and then the source and drain areas are P-type, and the channel becomes P-type. No, you're attracting positive charge carriers, but what happens is the voltages become reversed. So it's pretty similar to the NPN and PNP transistor. You reverse the voltages, you reverse the directions of current. We're not going to discuss the P channel much, no, because this is just an introductory course on Mos transistors. So all of the examples that are going to be given will focus on the N channel. The N channel is also a little bit better in terms of performance compared to the P channel, because the carriers in an N channel are electrons, and electrons are quicker to move than positive charge carriers. So this is just to summarize the operating modes of the MOS transistor. So there are actually 3 operating regions. The cutoff. In the cutoff, VGS is less than VTH, no, the threshold voltage, and I sub D is equal to 0. Okay. Then the linear region, or the resistive region, here VGS is greater than VTH, but VDS is less than VGS minus VTH. No? So VDS is less than VGS minus VTH, and I already gave you this formula. No? This is your expression for I sub T. And in the saturation region, that is when VDS is greater than or equal to VGS minus VTH. And you find that your current now is no longer a function of VDS. It only depends now on VGS. So these are the reference directions for current and reference polarities for your voltages. VGS is from gate to source. VDS is from drain to source. Now I have a question for you. What is the value of I sub G? If you take a look at this thing that I drew earlier, what is the value of I sub G? Anyone?
Zero,
Yeah, can you tell me why?
because of the insulator.
That's right, no? Remember, there's an insulator here. Okay. So if there's an insulator there, then the steady state value of this current would have to be 0. In other words, if this is DC, if you're applying a DC gate to source voltage, then the DC component of the current will always be 0. That's not true with AC. No, you're going to learn that later on. No? There's such a thing as displacement current when you apply AC. But in terms of DC, I sub G will be 0. Okay, and that's the nice thing about the MOS transistor. If I sub G is equal to 0, meaning whatever is applied, whatever voltage is applied to the gate, that voltage does not have to deliver any current. If it does not deliver any current, it does not deliver any power. No? So if it's not if the voltage applied to the gate is not delivering any power, then your circuit becomes very low, requires very low power to operate. And that's why the MOS transistor became quite popular. It's because it requires very low power to operate. Okay, so that's what I wanted to say here. For all modes, I sub G is equal to 0. If I sub G is equal to 0, okay, if you follow KCL, so just like the bipolar transistor, if you follow KCL, I sub G plus I sub D should be equal to I sub S. But if this is equal to 0, then automatically I sub D is equal to I sub S. whatever the current flowing into the drain, that will be the current flowing out of the source. Okay? Hindi kagaya nung bipolar transistor. In the bipolar transistor, if you will recall, the collector current is almost equal to the emitter current. No? The difference between the collector and emitter current is a small value, which is your base current. Well, here for the MOS transistor, what would have been equivalent to the base current, your gate current, is 0. And therefore, your drain current will always equal to your source current. Okay. So there are 3 operating modes: cutoff, linear, and saturation. The cutoff mode for the MOS transistor is similar to the cutoff mode for the bipolar transistor. When in the bipolar transistor, if your base emitter junction is reverse biased, yun yung condition for cutoff sa bipolar transistor, then your base current is 0 and your collector and emitter currents are also 0. Okay, you have the linear mode, no? The linear mode. Actually, ang nagiging similar sa linear mode sa MOS transistor is the saturation mode of your bipolar transistor. Okay, so if I compare the MOS transistor and then the BJT, so cutoff is the same as cutoff here, no? But linear here is what corresponds to, or what is closest to, saturation in the BJT, no? And saturation in the MOS, okay, is what corresponds to linear in the BJT. No, sorry, maybe better to use active, no? Active. Forward active mode, no? So here, active. So wag kayong malilito, no? Yung saturation sa BJT, ang katumbas nun, halos katumbas, no? Not exactly. But ang parang katumbas nun sa MOS is the linear mode or the resistive mode. And then the saturation in the MOS, what corresponds to that is the active mode. No? Active mode in the BJT. Okay, so if you take a look at your models, so these are now your circuit models. Okay, when VGS is less than VTH, what we call that? We call that cutoff. And this is how your MOS transistor looks like. Everything is an open circuit. Your gate is an open circuit, your drain is an open circuit, and your source is an open circuit. Again, no, just because it's an open circuit, that does not mean that VDS is equal to 0 or VGS is equal to 0. That's always a common mistake among students. No? Because it's an open circuit, your current is 0, but your voltages are not 0. Okay. If you take out the linear mode, okay, so when is it in linear mode? When VGS is greater than VTH, but VDS is less than VGS minus VTH, then this is your equivalent circuit. Your MOS between your drain and source looks like a resistor. Okay. So what is the approximate value of that resistance? Okay. If you take a look at your curve, so how did my curve look like? Like that, no? The approximate value is this slope. No? That's the approximate value of RDS on. No? This is the resistance from the drain to source when your MOSFET is conducting. But you will notice that actually, point by point, there's a different value of that slope. No? So if you try to approximate a slope for that entire linear region, this is what you'll get. But point by point, there is actually a different slope. No? So you might say this is a variable resistance depending on what your VDS is. And then in saturation mode, this is what it looks like. It is a controlled current source. That happens when VDS is greater than or equal to VGS minus VTH. It's a controlled current source. And your current is just a constant K multiplied by VGS minus VTH squared. No? By the way, no? Here, hindi ko linagay, no? But your current ID, anyway, this is 2K VGS minus VTH minus 1/2 VDS multiplied by VDS. Actually, from this equation, depending on the value of VDS, you can actually get a more exact value of RDS on. No? This is by differentiating this, by getting on the derivative of VDS with respect to ID. That's how you can get a value of RDS. No? But anyway, let's not go there. Okay, so those are your models. Those are your Mos models. Are there any questions so far? Any questions so far? Okay, so just like the transistor, I present, this is how I would suggest you analyze a Mos circuit. So the first thing you do, if you're analyzing a Mos circuit, is you determine VGS from the gate circuit, knowing that IG is equal to 0. Knowing that IG is equal to 0. No? You can compute for VGS. And then you compare the VGS to VTH. Pag nakita ninyo na yung VGS mas maliit sa VTH, agad-agad alam ninyo cut off yung Mos transistor. So ID is equal to 0 and IS is equal to 0. So you can now solve for all other quantities knowing that ID and IS are both equal to 0. Okay, pag nakita ninyo na hindi cut off, then ang unang pwede nyo gawing assumption, you assume that it is saturated. So you remember in the bipolar transistor, the first assumption that we always make is that the transistor is in the active region. So that IC is equal to beta times IB. So dito sa Mos transistor, okay, we assume that the transistor is in saturation. And therefore ID is equal to K times VGS minus VTH squared. So with this ID, you solve for VDS by applying KVL to the drain to source path. No? Compute natin yung ID, and then we compute for VDS by applying KVL to the drain to source path. Once we've computed for VDS, checkin natin yung assumption natin. Tignan natin kung totoo itong inequality na to. If VDS is greater than VGS minus VTH, then we know that our assumption is correct and that the calculated value of ID, the value that we calculated for ID is valid. No? Otherwise, if we find that VDS is less than VGS minus VTH, then the transistor is in linear mode. Kapag nakita nyo na in linear mode yung transistor, nagiging mas mahirap. No? Because now, you have two equations in two unknowns. You have this equation for ID, and then you have your KVL equation, and you have to solve for two equations in two unknowns to be able to determine the value of ID and eventually VDS. Okay. So what better way to illustrate these steps than through an example? So this is my example. So I had an example similar to this for the BJT. Let's do it again for the NMOS. Okay, so the Nmos transistor here, this Nmos transistor, has K equal to 0.25 mA per volt squared and has a threshold voltage of 3 volts. So I just want to fill out this table. Determine I sub D and V out for this various values of V in, where V in is actually the gate to source voltage. Pag tinignan nyo itong circuit na to, yung VGS is equal to Vn. And then I have another question. At what input voltage is the transistor at the transition from saturation to linear? So anong value of Vn, for what value of Vn, will the transistor be on the verge of shifting from linear to saturation, or from saturation to linear? Is it from from saturation to linear? Okay, so shout out na lang, no? For Vn equal to 0, what is ID?
0.
Anyone? Yeah, why?
Because there's no voltage.
I want a more exact answer, no? Why is it equal to 0?
Because it's cut off, sir.
Ano yan?
Cut off.
Well, the answer I was looking
Less
for is
than VTH.
exactly, yeah. That's the answer I was looking for, no? There will only be a current flowing in the channel, or there will only be a channel, remember, if V in is greater than or equal to VTH, no? So since V in is less than VTH, ang magiging sagot natin dito is 0. And therefore, what is V out? What is V out?
12 volts.
Yeah, this will be 12 volts. Okay.
So, sir, in your question earlier, the one where it's on the verge of going into saturation, that's when V in is 3 volts.
Mamaya muna, no? Mamaya muna.
Okay,
Let's tackle that later, no? Okay. Okay. So pag V in is 2 volts, okay. Ano yung magiging value ng ID?
Still 0.
0 pa rin, di ba? Because it is still less than VTH, no? And therefore, our output is 12 volts. Okay. Ngayon dito, no? V in is equal to 4. Mas malaki na yan sa VTH. So there are two possibilities. When V in is equal to 4, there are two possibilities. It's either linear or saturated. So since mas madali mag-compute kung saturated, umpisahin natin sa saturated. So we assume saturated. Okay, if it is saturated, what is our formula for ID? ID is equal to K times VGS minus VTH squared, no? What is K? K is 0.25 mA per volt squared, no? So let's stick to mA. So we'll assume that whatever value of ID we get is in mA. What is VGS? VGS is 4 because V in is equal to VGS. VTH is 3. No, VTH is 3 squared. So what is ID? ID is just 0.25 MA. Okay. If ID is 0.25 MA, what is V out?
Zero.
Ano yung value ng V out? If ID is 0.25 MA.
Sir, 11.5.
Yeah, that's right. No. So here you get 0.25 MA, and this is going to be 11.5 volts. No? How do I get 11.5 volts? I apply KVL to my drain to source path. No? So 12 volts minus ID times RD will be equal to V out. Okay? Pero hindi pa tayo tapos dito, ano? We have to check the assumption. Remember, we only assumed that it was saturated. How do we check the assumption? No? So, is 11.5 greater than VGS minus VTH? Is 11.5 greater than what is VGS 4 minus 3? And the answer is yes. No? So this is to check. This is to check whether it is saturated. The answer is yes. So that means that this is correct, no? So this means saturated. Okay? So ibig sabihin tama yung kinompute natin dito. Okay? So we can continue. We can continue. Okay, so ano yung next value? 6, no? So at Vin equal to 6 volts, okay, again, we assume saturated. So ID is equal to K VGS minus VTH squared. So that is equal to 0.25. What is VGS now? That's 6 minus 3 squared. No? So 0.25 times 9. What does that give me? 0.25 times 3 squared. This will give me 2.25 MA. Okay, and V out is going to be VDD minus ID times RD. So this is going to be 12 minus 2.25 multiplied by 2K. And this is going to give me 7.5 volts. Again, check. You have to check. Is 7.5 volts greater than VGS minus VTH? VGS is equal to 6, no? VTH is equal to 3. The answer is yes. Okay. So yes, so saturated pa rin, no? Saturated pa rin. So here, 2.25 MA, and this is 7.5 volts. Okay, punta tayo dito sa 8 volts. Sa 8 volts. Okay, at Vin equal to 8 volts, again, no, assume saturated. So what is ID? ID is now 0.25 multiplied by 8 minus 3 squared. 8 minus 3 squared. No? So K VGS minus VTH squared. So 0.25 times 25. Okay, so what will this be? This will be, Okay, I have, sorry, I have it pre-calculated in my notes, no? 6.25 MA. Okay. Let me compute for V out. V out is VDD minus IDRD, so this is 12 minus 6.25 multiplied by 2. And if I compute that, I'm going to get, notice that this is large, this is what? This is 12.5, no? Which is larger than this. I'm going to get minus 0.5. Negative. No? Pag nakakuha ka ng negative number, magduda ka na, no? Just like with the bipolar transistor, you cannot get a VCE that is negative if your supplies are positive. No? So here, we already see that this is wrong. No? Because V out, it is unlikely for V out to be negative if there is no negative supply in our circuit. And if you do the check, you're going to see that V out, okay, is going to be less than VGS minus VTH. Meaning to say, it is not saturated, no? It is linear. And therefore, mali. Hindi pwedeng tama itong value to. Okay? So how do we now solve for, how do you solve for I sub D? Okay, because you know that it is linear, okay, you'll have two formulas, no? Okay, first I sub D is equal to 2K VGS minus VTH minus 1/2 VDS times VDS, no? So this is 2 times, ano yung K? 0.25. VGS is V in, so this is 8 minus 3 minus 1/2 VDS multiplied by VDS. No? So this is one equation that relates VDS to I sub D. What is your other equation? Your other equation is, what is V out? V out is actually VDS. V out, which is VDS, is equal to VDD minus IDRD. Or VDS is equal to 12 minus ID multiplied by 2. So here I have two equations. Two unknowns. Okay. So ang problem natin nagiging math problem na lang, no? Two equations, two unknowns. Here I relate ID to VDS. Here I also relate ID to VDS. Okay. Unfortunately, well, fortunately or unfortunately, well, yeah, fortunately, if I express here, if I express VDS in terms of ID, substitute it back here, you can actually use your calculator's solve function to solve for ID. But you can also actually use simple math. No, you're going to end up with a quadratic equation somewhere here. Anyway, solving that simultaneously, okay, solving that simultaneously, what am I going to get? I'm going to get, okay, ID is equal to 4.73 MA and VDS is equal to 2.53 volts. That's what I'm going to get. So this is 4.73 MA. And this is going to be 2.53 volts. Okay, and you can do the same thing for 10 volts, and you can also do the same thing for 12 volts. No? So as an exercise, try to do the same thing for 10 volts, and then also do the same thing for 12 volts. No? Okay, that's probably all I should talk about now. Otherwise, baka ma-overload kayo. So just as an exercise also for you, subukan yung gawin yung number 2. Ano? At what input voltage is the transistor at the transition from saturation to linear? No? So it's somewhere between 6 and 8. It's somewhere between 6 and 8. No? At 6 volts dito, we are still in saturation mode. Pero dito sa 8 volts, we are already in linear mode. No? So try to figure out what voltage between 6 volts and 8 volts was that transition, kung saan siya nag-shift from saturation to linear. Now, with regard to the earlier question, I think there was a question, what happens at 3 volts? Well, 3 volts is the other transition. No? 3 volts is when it transitions from being cut off to saturation. No? It transitions from cut off to saturation because when Vin is less than 3 volts, the current is equal to 0. When Vin is greater than 3 volts, okay, your current becomes greater than 0. And since VDS is most likely going to be larger than VGS minus VTH, then that's almost surely going to be in saturation mode. Somewhere in between these two, it transitions to saturation, and that is when VTH is equal to 3 volts. So try to do that on your own, and then we'll continue the discussion next time. Okay, are there any questions? Any questions? Okay, again, yung there's a question about Thursday. Kailan ba umpisa ng reading break? '29, no? So yeah, so it looks like we won't have any synchronous session on Thursday, no? If your reading break starts on the 29th, no? We'll resume the synchronous session pag no? Otherwise baka magalit kayo sa akin. Okay? So you're going to see, I'm going to send you these annotated slides. You're going to see the rest of my slides, I guess. So you might also want to take a look at it. No? But note that yung una kong diniscuss sa inyo, lahat nitong drawings na to, no? These drawings that I presented to you, that's not really part of the coverage. No? You don't really have to master this. The only reason why I presented this to you was I wanted to give you more insight on how the Mos transistor work. Okay. So if there are no questions, then officially that ends our synchronous session. I will close the session as soon as the last person has left the Zoom session. Okay, thank you.